Hello, today class is about CMOS inverter. Complementary metal oxide semiconductor field effect transistor inverter. So here I am going to design a inverter circuit using CMOS transistors. Right. Next, going to the next slide. Here the term CMOS stands for complementary metal oxide semiconductor. So this CMOS technology is one of the most popular technology in designing the computer chip and broadly used today to form integrated circuits in numerous and varied applications. So in many applications related to the integrated circuits, the CMOS technology plays a key role in it. Okay, today's computer memory, central processing units and cell phones makes use of this technology due to several key advantages. So what are those key advantages for the CMOS inverter is it has low power consumption, it has low power consumption, speed of operation is very high and complexity of the circuit is less, which we have discussed these points in our introduction video. Okay, this CMOS plays a key role in designing the integrated circuits. So this technology uses both the P channel as well as N channel semiconductor device. So we can say that the CMOS inverter is nothing but the combination of PMOS as well as NMOS. If you see the picture clearly here, this is PMOS transistor and this is NMOS transistor. If you combine these PMOS as well as NMOS, we will get this complementary metal oxide semiconductor inverter. In PMOS transistor, so I said that for any MOS fabrication, the substrate should be opposite to that. In PMOS, N well has to be used. In NMOS, P substrate is used. In NMOS, N diffusion should be there, which can act like drain and source. In PMOS, P diffusion should be there, source and drain. And this polysilicon material, which can act like a gate. And this circuit, transistor circuit, is a latch-up circuit. Next, CMOS inverter. If you see the picture very clearly here, this is a CMOS inverter, which is a combination of PMOS as well as NMOS. If you see the picture clearly, this one is a PMOS or pull-up transistor. This is a pull-up one and pull-down, which we have discussed in our previous video about pull-up transistor as well as pull-down one. Okay, this CMOS is a combination of PMOS as well as NMOS, where the upper part is a pull-up one and lower one is a pull-down one. Okay, it is a combination of, this is a PMOS, P channel MOSFET, and this is N channel MOSFET. Now I am going to combine both the gates of PMOS and NMOS into a one element, which is considered as input. Between these two combination, there is one node where I am going to take a output at there. So if you see the picture clearly of these transfer characteristics, when this x-axis is an input 1 and y-axis is output 1. So under the x-axis, when input is 0, see over there, Vout is at approximately equal to VDD. Is it clear to you? Right. When the input voltage is at 0 potential, here what the cursor is showing now, this is 0 volts of input, the output is at maximum VDD. So simply it is inverting the 0 level to 1 level. So it is performing its action. so it is acting as an inverter. So I repeat, when I am giving an input voltage of 0 here, the output is at VDD. When the input is at VDD, output is at approximately. Okay, if you see the picture clearly here, when the input is at 0 volts, the output is at VDD. When the input is at VDD, the output is at 0 potential. Okay, during between these two, there is a transition state which is displayed in this picture with a line both are on. So under the state from 0 to logic 1, the PMOS is on and NMOS is off. So under the logic from 0 to 1 state, so PMOS is on and N is off. And when it is changing from 1 to 0, N is on and P is off, which I have written here. So between these two states, there is a transition state. Under that transition state, both are in saturation and both will be in turned on. So if you see this picture clearly, this is a circuit and the internal circuit is this one. If this is a picture of CMOS inverter, the internal circuit shows this one. So when the input is at logic 1, this is when Vin is VDD. When the input is at logic 1, the PMOS transistor will be turned off. And the NMOS offers a resistance. So therefore the VDD is not going to get here. Why? Because there is no contact between VDD as well as V out here. Is it clear to you? I repeat, when Vin is equal to VDD, when I am applying Vin is equal to VDD, VDD means plus 5 volts or logic 1. I am applying logic 1. So when input is at logic 1, the PMOS transistor, so this is the PMOS one, the PMOS transistor will be turned off. Why? So when I am giving 1 here, this PMOS is the complementary of NMOS, so 1 becomes 0, so this will be in cutoff. So that's the reason here open circuit. So when input is at logic 1, the PMOS transistor will be in turned off and NMOS offers a resistance and thereby providing an output voltage of 0 volts since VDD is not connected to Vout. So quite opposite to the second one, when input is 0, when I am applying a 0 volts here, this N will be in cutoff and P will be in saturation. So this is P will be in the linear mode or saturated mode and N will be in cutoff. So when the input is at logic 0, the NMOS will be in turned off and PMOS offers some resistance RP. Therefore this VDD will drain out to this point V out with respect to ground. Then we will get the V out is equal to plus 5 volts or plus VDD. So when I am applying a logic 0, to the second case, I am getting logic 1 or plus VDD at this output. But here this is the converse of this one or reverse of this one. When I am applying a logic 1 here, what happens? This is open circuit, therefore VDD will not going to exist at this point V out. Okay. Next, in going to the regions of operation of complementary metal oxide semiconductor inverter. So this is very important. So let us discuss about these regions of operation. It is going to work in 5 regions. So I am drawing a graph between input as well as output voltage. So the same graph is there here. This graph, whatever the graph which is there here, transfer characteristics, I am simply replicated here, but some modifications has been done over there. Okay, see here at 0 Vin. So wherever this is x-axis and this one is y-axis. So at x-axis is input When input is 0, the output is VDD. When input is VDD, the output is at 0. So simply inverting. It is when when Vin is 0, the output is VDD, means logic 1. When Vin is VDD or plus 5 volts, the output is at 0 potential. Simply it is complementing the input at the output, or simply toggling from 0 to 1 state as well as 1 to 0 state. So here 5 regions is there: region 1, region 2, region 3, region 4 and region 5. So what will happen in the different regions of their operation? So in region 1, what is happening? This region is about the voltage range between 0 to Vt. 0 to Vt. So 0 to Vt means it is not existed at the threshold point itself. So what happens when the input voltage is less than V threshold? Definitely we can say that it is in cutoff mode. The NMOS will be in cutoff mode. When the NMOS transistor will be turned on? When it exceeds the threshold voltage only. Okay. So what happens in the region of input between 0 to Vt? Between the region 0 to Vt, the input voltage will be less than V threshold. Therefore, the NMOS will be in cutoff. So no current will flow from VDD to Vs. So therefore the entire VDD will appear at the output. The entire VDD will appear at the output. So between the region 1, between 0 to V threshold voltage is the region 1. Between 0, VSS is nothing but 0, don't get confused. Between the region 0 to VTN is the region 1. So this VTN implies NMOS threshold voltage. So when the NMOS threshold voltage is greater than VGS, then definitely it will be in then definitely the NMOS transistor will be turned on. But here what happens? It is less than V threshold voltage. Therefore T1 transistor means T1 transistor. So this one is T1 transistor and this is T2 transistor. Okay, the transistor T1 will be turned off and T2 will be in linear region. So linear means resistance region. So if you see this picture, so when it is turned off, it will offer some resistance, linear. So that is all about region 1. So what happens in the region 1 means, I repeat, between the threshold voltage, so it is less than threshold voltage, definitely NMOS will be turned off, or when NMOS will be in cutoff region. Therefore T2, so the upper transistor will be in linear region. Therefore the total VDD will exist at the output. So that is written here, in this region 1. Clear? Region 2. In this region is all about between VTN to VDD by 2, half of the VDD to VTN. So above the threshold voltage of NMOS to the maximum voltage, half of the maximum voltage, or VDD by 2. So what happens in this region? The input is in the region VT to VDD by 2. Since the input voltage is greater than V threshold voltage, but here it is less than threshold voltage. That's why NMOS is in cutoff. But here the input voltage is greater than Vt. Therefore the NMOS is conducting. But here NMOS is cut off since the input voltage is less than V threshold voltage. Therefore the NMOS is in cutoff region in the case of region 1. But here the input voltage is greater than Vt. Therefore NMOS is conducting and it jumps to saturation. And the PMOS will remain in linear region itself. So it will be in linear region itself. So that's the thing I have written here in the case of region 2. T1 will be in saturation. T1 means the lower one, the lower N channel one, and T2 means the upper one, P channel one. Okay, this is pull up and pull down. Pull down is T1, pull up is T2. So what happens in this region? between VT2 VDD by 2. VT2 VDD by 2. T1 will be in saturation. Why it comes to saturation? Since the input voltage is greater than threshold voltage. Therefore, the NMOS is conducting and it jumps to saturation, but PMOS will be in the linear region itself. Clear? Next, in going to the region 3, this is region 3. This region 3, in case of region 3, is the voltage at the point VDD by 2. At the point VDD by 2. So at this point, the output voltage is also VDD by 2. If you see the picture very clearly here, at this point of intersection or region 3, the input and output is equal. So the input is VDD by 2 and the output is also VDD by 2. If I draw a line perpendicular to the x-axis, perpendicular to this x-axis, I will get VDD by 2. So that's the reason in the region 3, input is VDD by 2. At this point, V out is also VDD by 2 as shown in the figure. So which I am showing here. This is VDD by 2. If I draw a line perpendicular to this, I will get VDD by 2 itself here also. So at this mode, both NMOS and PMOS are in saturation. Both NMOS and PMOS are in saturation. So both will be in saturation. So that's the reason I've written T1 is at saturation, T2 is also at saturation. Next, in going to the region 4. In this region, the input voltage is between VDD by 2 to VDD minus V threshold of PMOS. Okay, this is the region. Region 4, VDD by 2 to VDD minus V threshold of PMOS. V threshold of PMOS. So it will be in the converse of region 2. So this it will be in the converse or reverse order of region 2. So in the region 2, what happened? T1 is in saturation and T2 is in linear, but here it will be in the opposite direction. So T1 becomes linear and T2 will be in saturation. Okay. In region 4, the input voltage is in the between VDD by 2 to VDD minus VTP. Here the PMOS remains in saturation and NMOS moves from saturation to linear region. Since the drain to source voltage is now less than VGSN minus V threshold voltage of N channel. So it will be in the converse of region 2. So in region 2, T1 is at saturation, T2 is in linear. So after crossing the region 3, the direction will be in reverse and T1 will gets linear and T2 will remains saturation. So in going to the region number 5. In this region, this is all about in the region between VDD minus VTP to VDD. So VDD minus VTP to VDD. And this will be in the converse of reverse one. This will be the reverse order of region 1. So in region 1, T1 is off, T2 is linear. So it will be reversed in region number 5. Okay, T1 will be in linear and T2 will be in off. See carefully. So region 1 and region 5 are opposite in direction. Region 2 and region 4 are also in opposite with each other. But wherever the region 3 is there, under the region 3, both the transistor will be at saturation. Okay. Right. In going to the region 1, I repeat, region 1 is between 0 to VTN. So this voltage is less than threshold voltage. Therefore, the T1 will be off. T1 means this one, lower one. Why? Because the threshold voltage is lesser than the VGS value. So we can say that this will be in cutoff state and this will move to linear state. So that's the thing I have written here. So in the case of region 2, what happens? In region 2 is all about the voltage between threshold voltage to the VDD by 2. So it exceeded the threshold voltage. When it exceeds means definitely the transistor T1 will starts to conduct. So while conducting it will move to saturation mode and T2 will be in linear itself. So in going to the region 3 it is VDD by 2. Both will be in saturation. Region 4 is the reverse order of this region 2. So what happens? T2 will get into saturation and T1 will get into linear. And region 5 is the opposite of region 1. So what happens? This T1 will goes to linear mode and T2 will be in turned off. So this is all about the regions of operations in CMOS inverter. Right, clear? Now there is one drawback in the CMOS inverter, which is a latch up. So this is also the important thing you have to be remember. Okay, latch up. What is this latch up? A latch up is a condition in which the parasitic components means parasitic capacitance, as we discussed in our gate capacitances or MOSFET capacitances. Parasitic capacitance means the capacitance offered by the MOSFET, which will be in the order of picofarads, means into 10 to the power of minus 12, or nanofarads, which will be in the order of 10 to the power of minus 9. So the negligible one, but this negligible one is also affecting the CMOS inverter action. So that is latch up. A latch up is a condition in which the parasitic components gives rise to the establishment of low resistance conducting path between VDD as well as VSS with disastrous results. So what is VDD and what is VSS? These are both supply rails. So if you see this picture, the biasing voltage is VDD and ground potential is VSS. These are the two supply rails. Between these two supply rails we are drawing the circuit. Okay, in going to the latch up is a condition in which the parasitic components gives rise to the establishment of low resistance conducting path between VDD and VSS. So it offers a low resistance path between VDD and VSS. Low resistance means high flow of current will flow from VDD to VSS. So and it makes a faulty readings, or otherwise it makes a disastrous results. So a problem which is inherent in P well and N well is due to the relatively large number of junctions which are formed in these structures, and as mentioned earlier, the consequent presence of parasitic transistors and diodes. So this problem is an inherent in one. So in the P well and N well process is due to the relatively large number of junctions which are formed in these structures, as mentioned earlier, the consequent presence of parasitic transistors and diodes. So this latch up may be induced by glitches on the supply rails or by incident radiation. This will occur due to glitches on the supply rails, or maybe it may be an incident radiation. If you see this picture, this is our CMOS transistor with P well process. Okay, this is a P well process of CMOS, where I am going to use a N type substrate here. So what about I said this is the latch up is due to the parasitic components, and that gives rise to a low resistance path between the two supply rails VDD as well as VSS, and it will make a faulty readings or the disastrous results. A problem which is inherent in the P well and N well is due to relatively large number of junctions which are formed in these structures, and as mentioned earlier, the consequences present in parasitic transistors and diodes. So this one, transistors and diodes. Okay, latch up may be included by glitches in the supply rails. So it may be induced due to some glitches in the supply rails or by an incident radiation effect. So here if you see the picture here clearly, this is the latch up effect in P well structure. Latch up effect in P well substrate. So there are two transistors. There are two transistors and two resistors. See here, two transistors are T1 and T2, and two resistors RS and RP, which are associated with the P well and with the regions of this substrate. These are associated with the with the P well, it is associated with the P well. We see RP and T2 is associated with the P well, and T1 and RS is associated with this N substrate. And this which forms a path between VDD and VSS. See here, this is VDD. VDD is connected to T1 and RS, and this T1 and RS is connected to RP and T2, and it is connected to VSS. So the same point he discussed here is this is associated with the P well and with the regions of substrate, with the regions of substrate, and this which forms a path between VDD and VSS. Is it clear? It is forming a channel or path between VDD and VSS. This VDD T1 RS conducting and RP T2 is conducting VSS. So the current flows like this: VDD T1 RS, next RP T2 and VSS. So simply, as I discussed, a low resistance path here. This is nothing but establishment of low resistance conducting path between VDD and VSS. Establishment of low resistance conducting path between VDD and VSS with a disastrous results. Low resistance path means free flow of current will flow from VDD to VSS. So the same thing is seen here. VDD, this is VSS. So the path is low resistance. Why? Because if this transistor or passive components will be not there, definitely it offers some high resistance. But here what happening, VDD is connected to this T1 RS circuit, and next this is directly connected to T2 RP and VSS. So therefore, which forms a low resistance path or easily path between which offers a low resistance path between VDD and VSS. So this thing means current VDD T1 RS RP T2 VSS that I was highlighted in this establishment of low resistance conducting path between VDD and VSS. So that was seen here: VDD T1 RS RP T2 and VSS. If sufficient substrate current flows to generate enough voltage across RS to turn on the transistor T1, Okay, there will be a sufficient free flow of current that will sufficient current will be there that will be enough to turn on this transistor T1, and this T1 then draw current through RP. So we see here, if it is turned on, definitely it will draw current like this directly to RP. So what he is saying is, if sufficient substrate current is there, so it is enough to develop a voltage across RS. If current is there and here resistance RS, so I into R, if current is there, this is resistance RS. If I multiply I into R, there will be a voltage drop. This is voltage across RS. Okay, and this will turn on the transistor T1. It will turn on the transistor T1, and this will draw a current directly to this P well. This will draw current through RP. So RP. So similarly, T2 will be also turned on. Okay. So establishing a low resistance path between VDD and VSS. Therefore, the total gain becomes B1 into beta is equal to 1. So latch up will occur. So I repeat, so our latch up is establishing a low resistance conducting path between VDD and VSS. So if you see here, there are two transistors and two resistors, T1, T2 as well as RS and RP. Okay, this RP and T2 associated with the P well, and T1 and RS is associated with this N substrate. Okay, what happens is, if a substrate current is there, if there is a sufficient substrate current, that current is multiplied with resistance Rs, so there will be a voltage drop across it. So that is voltage across Rs. This Rs will turn on this transistor T1, so total short circuit, and that current will flow to Rp. So there will be a current flow through Rp, which in turn will turn on this transistor T2 also. Thereby, a low resistance path is generated between VDD and VSS. I repeat, if sufficient amount of current in the substrate is there, that will make a voltage across this Rs. So when the voltage is across this Rs is greater than the cut-in voltage of this transistor, it will be turned on and it moves to saturation mode or linear mode. So when it is turned on, definitely it will drain some current, and that current will pass to this Rp and T2. Therefore, this T2 will be also turned on. So the total this circuit is there, RST1, RP22 will be turned on. Therefore, this total circuit will offer a low resistance path between VDD and VSS, and it may cause to a disastrous results. So this process is considered as latch up, and therefore the total current gain beta 1 into beta 2 should be equal to 1. So whatever the circuit is there here is represented here. This one is the latch up circuit model. So that is also represented with this diodic symbol. Okay, is it clear to you? Right. Now what I have to do when there is a latch up problem in CMOS? So what should I do? Means simply follow these remedies for the latch up problem. So increase the substrate doping level with a consequent drop in the value of Rs. So simply increase the doping level. Next, reducing the value of Rp. So by control of fabrication parameters or ensuring that low contact resistance to VSS, and other more elaborate measures such as introduction of guard rings. So introduce guard rings is the first remedy. Second one is reducing Rp, and third one is substrate increase in substrate doping levels. So these are the 3 points. So first we can increase the substrate doping level, then we can reduce the latch up problem, and by reducing the value of Rp also we can reduce the latch up, or by introducing the guard rings we can reduce this latch up problem. Okay, so this is all about CMOS inverter. Okay, thank you very much.